Lecture 4.2, Mean Value Theorem for Derivatives. This photo and the next two were taken at different times at Theodore Roosevelt National Park in North Dakota. This shot was taken with only slight magnification from the window of our minivan. These are a couple of teenagers showing off for the girls. Here are a couple of older bison. Some people have said that they thought this photo looked fake, but this was actually taken through the windshield of our van. And when this happens, your choice is to wait. They move when they want to move. And this last photo is of a cedar waxwing, also taken at Theodore Roosevelt National Park. The mean value theorem for derivatives. If f of x is continuous over closed interval ab and differentiable over interval ab, then at some point c between a and b, f prime c equals f of b minus f of a over b minus a. The mean value theorem only applies over a closed interval. The mean value theorem says that at some point in the closed interval, the actual slope equals the average slope. In this example of an arbitrary function y equals f of x, if we consider 2 points a and b, the slope of the chord between points a and b is f of b minus f of a over b minus a. That is change in y over change in x. And we see that there's a tangent parallel to the chord at some point between x is a and x is b. The slope of the tangent is the first derivative, f prime of c. Increasing and decreasing functions. A function is increasing over an interval if, when x1 is less than x2, then f of x1 is less than f of x2. A function is decreasing over an interval if, when x1 is less than x2, then f of x1 is greater than f of x2. Note, increasing does not mean that the derivative is always positive. Decreasing does not mean that the derivative is always negative. In this example, y equals x cubed plus 1 over the interval from negative 0.05 to positive 0.05. This is an increasing function because as we move to the right, the y value is always increasing. Even though the derivative is 0 at the point where x equals 0, the function is still increasing. The terms increasing and decreasing refer to intervals, not to individual points. For the function y equals negative x squared plus 2, which we recognize as a parabola opening downward and shifted up 2 from the origin, the function is increasing on the interval from negative infinity to 0. And notice that we used the brackets on the right-hand side to show that the 0 is included. This function is decreasing on the interval from 0 to infinity, and we notice that 0 is included in the decreasing interval as well. 0 can be in both intervals because both intervals satisfy the definition of increasing or decreasing. Once again, looking at our arbitrary function, we notice that these two functions have the same slope at any value of x. Functions with the same derivative differ by a constant. And it doesn't matter where we measure, as long as we measure vertically, the distance is the same. Example, find the function f of x whose derivative is sine x and whose graph passes through 0, 2. The derivative of cosine x equals negative sine x. So the derivative of negative cosine x equals sine x. F of x could be negative cosine x or could vary by some constant c. Therefore, f of x equals negative cosine x plus c. However, we have some initial values. So if we plug in 0 for x and 2 for y, or f of x, then we can solve for c. So 2 equals negative cosine 0 plus c, or 2 equals negative 1 plus c, so 3 equals c. Our original function then must have been f of x equals negative cosine x plus 3. Notice that we had to have initial values to determine the value of c. The process of finding the original function from the derivative is so important that it has a name: the antiderivative. A function big F of x is an antiderivative of a function f of x if big F prime of x equals f of x for all x in the domain of f. The process of finding an antiderivative is antidifferentiation. You will hear much more about antiderivatives in the future. This section is just an introduction. Example 7b. Find the velocity and position equations for a downward acceleration of 9.8 meters per second squared and an initial velocity of 1 meter per second downward. So our acceleration is 9.8 meters per second squared, and we'll let down be positive. Since acceleration is the derivative of velocity, velocity must be the antiderivative of acceleration. So we get v of t equals 9.8t plus c. We can check that by going backwards. The derivative of 9.8t would be 9.8. And of course, the derivative of a constant is 0. We have an initial velocity of 1 meter per second downward. So we enter our initial values, and we get 1 equals 9.8 times 0 plus c, or 1 equals c. So our velocity equation is v of t equals 9.8t plus 1. Since velocity is the derivative of position, position must be the antiderivative of velocity. So we take the antiderivative of the velocity equation, and what we're doing is using the power rule in reverse. So we increase the exponent by 1, and then divide by the new exponent. And of course, because the derivative of t is 1, then the antiderivative of 1 must be t. And remember that there could be a constant. So once again, what we've done is use the power rule in reverse. We increase the exponent by 1 and multiply by the reciprocal of the new exponent. So we get s of t equals 4.9 t squared plus t plus c. The initial position is 0 at time 0. So we plug in those initial values, and we find that this c equals 0. Note this is not the same c we used earlier. So our position equation is s of t equals 4.9 t squared plus t. And these are our three equations.